It's my great pleasure to open this series of our research seminars with a talk of Professor Suragan from Kazakhstan, Astana. And the title of the talk is here. So thank you very much for agreeing, Professor Suragan, Durvudkhan Suragan, to present a lecture at our seminar. And please go ahead.
Thank you. Thank you for your kind introduction, and thank you for this invitation and opportunity to present our work. So the aim of this talk is simple. It's about presenting unified approach to obtain all Hardy type inequalities, all basic inequalities, function inequalities in variable space. So there are two parts. First part of this talk is about our published work with Professor David Cruz Urube, University of Alabama. This part, Hardy-Leray type inequalities in variable Lebesgue space. This work was published. And the second part is about similar results, but in variable Morrey space. So second part is our ongoing work. So it's in progress. If time permits, by the end of this presentation, I will shortly describe our main result in that field. So here, speaking about second part, we have another collaborator, Arash Korbanalizadeh, from Institute of Advanced Studies in Iran. So the second part, we are doing the second part of this work. So as their name implies, the variable Lebesgue space generalization of classical Lebesgue space. Just technically, one needs to replace those constant exponents which appears p's, which appear in the definition of classical Lebesgue space, by a function. We call this function special function an exponent function, and intuitively, variable Lebesgue space set of all measurable functions for which this given integral is finite. So this is very rough intuitive idea, and indeed, if one introduce the following Luxembourg norm, so here we have in curly brackets, we have a so-called modular functional, and if we require this modular functional, then the infimum indeed gives the norm of variable Lebesgue space, and one can easily see, for example, if here in modular functional, if here we have some constant, then what appears in the numerator will not depend on x, so easily 1 over lambda to p can be written in front of this integral, and then one can multiply by that both sides of this inequality. So indeed, in that case, it follows that the infimum of those lambdas indeed the classical Lebesgue norm, LP norm. So one can see from this simple definition, one can see that indeed there is a classical Lebesgue space in this definition. Also, here this exponent function can be indeed unbounded, but in this presentation I didn't want to go into details. It can be unbounded if in that case one needs to modify the expression for a modular functional, and so still, even if a function, this p exponent function is unbounded, then there is one can define variable Lebesgue space. Moreover, one can use some general modular functional here to obtain more general function space. So this class of function space can be considered as as part of such a general function space, but we are interested in our focus is only about variable Lebesgue space, and because of it, it has applications, and especially in PDs and calculus of variations. When there are functions with so-called non-standard growth, then this theory plays important role there. And there's an excellent book about variable Lebesgue space. All details can be found there. So returning back Hardy inequalities, as I mentioned, our idea first, the very first motivation was to obtain standard direct generalization of Hardy inequality in a variable Lebesgue space. And when we found out that there's no so-called Hardy-Leray inequality in variable Lebesgue space, we were surprised, but we thought maybe, well, these inequalities are there because both topics are, very well-known topics, and so our starting point was one-dimensional Hardy inequalities. So we found these literature, so Kokilashvili, Samko, Deaning, they started obtaining such inequalities, Hardy type inequalities, but in one-dimensional case. And then later, a multi-dimensional case, a multi-dimensional Hardy inequality was obtained, but in so-called geometric version. So multi-dimensional case, there are several formulations. They are not equivalent formulations of Hardy inequalities. So this formulation, when we have a weight here, which is about distance to boundary, and this formulation is about bounded domains. Everywhere we assume that f is a smooth function, but one can use density arguments to reformulate these inequalities in solvable space, for example. But the point is that Hardy inequality multidimensional version was obtained by these authors, and there's another type of Hardy inequality also obtained by Rafero and Samko. But these are not cannot be considered as Hardy-Leray because we want to see on the left-hand side usual distance, Euclidean distance, as weight in the numerator and in whole space. So we were interested in that formulation. And speaking about other works in this field, for example, Hardy-Sobolov inequality without weight on the left-hand side. Without weight, these inequalities were obtained by the same author, the Cruz, Fiorenza, and also recently some weighted version was obtained by Edmonds and Miskey, and these are well, these are not Hardy-Leray inequality. So we call the following formulation the Formula 1 Hardy-Leray inequality. So here important thing is that we have on the left-hand side this distance, normal Euclidean distance as weight, and well, this inequality has long history. It started by, well, even before Hardy, people, some discrete versions obtained it, but Hardy published the one-dimensional version of this inequality, and then later it was extended to multidimensional case by Leray. Here the P is less than N. It's important because in critical case, one can simply show that indeed this inequality does not hold. So one can, it's two-line proof that such constant. The important thing is that, of course, in this classical case, sharp constant is known, and it depends on P, but the important thing is that the constant shouldn't depend on F. So critical case is not, this doesn't hold, but one can replace the weight on the left-hand side by some logarithmic weight. But still, the inequality holds when, even if this P is greater than N. So N is our dimension of space. So that's starting point. Well, historically, that's a very early stage, and then later it turned out that such inequality has many applications in PDE. For example, if we consider these basic second-order partial differential equations, then the elliptic, parabolic one, and hyperbolic one on the left-hand side, linear part, and on the right-hand side, if we consider this with this special term on the right-hand side, then Hardy inequality can be applied to obtain results about existence, non-existence. Indeed, that sharp constant gives important information about existence. And so I took this from Professor Nadir Masmoudi's paper that, well, most mathematicians would agree that Hardy inequality is one of most probably important inequalities in analysis, as well as the Sobolev inequality. Interesting fact is that Sobolev inequality can be derived from Hardy inequality, but still they are independently important. So these are just for introducing the topic to those, well, these facts are well-known ones, but to those distant from this field might be interested in this starting motivation part. Nowadays we have more general inequalities, and one of them, well, which covers both Sobolev inequality, Hardy inequality, and including some critical cases as well. So one of them is so-called Kafarelli-Nuremberg inequality. So special two-weight inequality, but the power weights, and so this is important inequality, and indeed, well, similar results hold for the fractional powers of the Laplacian. And well, one can, as you see on the right-hand side, we had the one can have a gradient or higher order say Laplace. When Laplace appears on the right-hand side, this inequality is called relief inequality, but one can replace those operators by fractional one, and in these GFA papers, well, there are many sources, but here I've chosen these two papers, and one can see interesting discussion about fractional Hardy-Leray inequality in the first paper of Frank and Thiringer, and the exact fractional full range Kafarili-Nürnberg inequality. So as I know, this appeared first in this second GFA paper with in this form. So we are going to generalize all these inequalities in variable Lebesgue space. So we're going to now replace the Q here by some Q of X function, here P, some P of X function, and then to see how all these assumptions, these ones, the essential ones, by the way, one can prove. I'm not sure about fractional case, but this classical case, there's conditions to they are also this is one can prove that the reverse argument and defend only. So these conditions are essential ones. Here, just to recall fractional Laplacian. So the question we asked was the following: are Hardy-Leray inequalities in variable Lebesgue space valid? That was in this form. So I've just mentioned. So in the form 1, is it? So can we obtain the direct generalization of this inequality? That was a first question. We were doing. I was visiting University of Alabama after the pandemic, so we were doing something with David. We were doing working on some different topic, but we thought, well, this question is answered, but it turns out that at least we couldn't find the Hardy-Leray inequality in variable Lebesgue space. So we decided maybe it's to write a paper on it. So this is our answer, and here we have we believe this condition here. LH means log Hölder continuous. I'm gonna give definition of that, recall definition of that class. And the first is just measurable function. It's essential one, and we also believe that the second assumption is also essential. And those experts in this field, it's for them it's clear why we have it, because it's about harmonic analysis, and it's important to do harmonic analysis in Lebesgue. Variable Lebesgue space, so under log Hölder condition, because the boundedness of, for example, maximal operator is about this condition, and so on. So since we now, instead of P, we have a function, exponent function. So one can define infimum, essential infimum, and essential supremum of that function. So again, this is essential range between 1 and then for all smooth functions we have this desired inequality, and it's indeed Hardy-Leray inequality in variable Lebesgue space. So just to recall that a log Hilder continuous function. So to define log Hilder continuous function, we need to first recall the definition of local log Hilder continuous functions and global log Hilder continuous functions. So local means that the given function must satisfy this inequality, and global means that it's about for all. So here for local condition we are in ball of radius 1/2 centered at y, right? But about global one we don't require any. So for all x, so if given function p measurable, then measurable Lebesgue, of course, and satisfies both these conditions, then we say that function is from LH class, so a log Hilder class. So what we have here is indeed that condition. So again, it's essential one. So proof idea is also simple. Our main idea is to obtain Stein-Weiss inequality, so from Stein-Weiss to derive all other those mentioned inequalities from this one, to obtain the Stein-Weiss inequality, and then to derive the other inequalities from the Stein-Weiss inequality. So in other words, we suggest this unified approach. So we have simple algorithm, and that indeed that gives all inequalities, and proof details are given in our paper. It's published in GMA, and well, we were trying to prove this Stein-Weiss inequality first in variable Lebesgue space. We didn't know this work well when we started this project, but we were using previous works of Samko and the other mathematicians, but here, for example, in Samko's paper, some Stein-Weiss inequality is obtained in Lebesgue space, variable Lebesgue space, but only for bounded domains. And in second paper, these authors they proved the Hardy-Littlewood Sobolev inequality, not the with the weights. So we needed to have the following. We needed to have a Stein-Weiss inequality with two weights power. These are inequalities, two-weight inequalities with power weights. But later we discovered that indeed these authors they obtained in this paper more general inequality, and the desired Stein-Weiss inequality can be obtained as consequence corollary from their work. So in that sense, we were quite lucky, because what we needed were in this paper, and then the rest is not. It's simple, and as long as you have Stein-Weiss inequality, then. So indeed, this theorem I showed here is a particular case, as in classical case, right? In classical case, we started with Hardy and then Sobolev, and then indeed Kazakhstan Nuremberg inequality course of both Hardy and Sobolev inequalities. So here the situation is the same. So we have a Kazakhstan Nuremberg inequality in a variable Lebesgue space in this form. So it's formula 5 here. So as I promised, so we replace those exponents by exponent functions. Okay, now we have a variable Lebesgue space, and these p and q functions, exponent functions, they are from the same class, which I explained. It's about log Hölder continuous function class, and well, under the essential conditions, and we have a Kazakhstan Nuremberg inequality in variable Lebesgue space. Proof is incredibly, it's short, surprisingly short, just one line. So this is our proof, one line proof. And so first inequality is about pointwise inequality. Indeed, these variable space, they enjoy nice order preserving property. It's, well, it's about if a positive function is bigger than another positive function, then their variable Lebesgue norms are also greater than the variable Lebesgue norm of the second function, right? So the order preserving property gives, well, combined with pointwise inequality. So here, if we compare these two norms, first two norms, then here indexes there's the same q, and also we have the same weight. Only change here is that we replace f by here I1 is risk potential. So here we have definition at the end of this page. We have definition of well, formula for this notation I alpha. So if we're flagging there instead of alpha 1, then for, well, it's almost everywhere you have a pointwise inequality. So since you have pointwise inequality, and since these variable order variable Lebesgue space, they have this, I've just mentioned, they have a order preserving property. So the first inequality is almost for free. So we got this first inequality with some constant. These are two different constants, of course. And then the second inequality is indeed about what I said. It's about Stein-Weiss inequality. So this inequality here is called Stein-Weiss inequality, and this is the theorem we derived by using previous work. And so our suggestion is the following. So here we have, of course, a variable Lebesgue space, but all these type of space now, I'll also, if time permits, shortly mention our result in variable Morrey space, but our suggestion unified approach our suggestion is the following: to obtain this inequality in the function space, and then to derive the other Hardy type inequalities from this inequality. So that's, well, more or less this fact. Whereas I think this approach was known, but we are developing this idea and completing those gaps in, for example, in variable Lebesgue space. So this is the proof idea. So simply we get Kaforelli-Nuremberg inequality, and then from Kaforelli-Nuremberg inequality to get it's part Hardy inequality. Hardy-Leray inequality is particular case. So that's the proof idea. But disadvantage of this approach is that advantage is it's simple and I would say good project for good PhD students in analysis, depending on space. So because problem is there, but it's a simple advantage, I would say, and unified approach, and it gives almost all fundamental inequalities. But the disadvantage is that with critical case, for example, maybe you have noticed here in classical case, for example, in classical case, one can include here 1. But in our case, our approach, unfortunately, doesn't give such a critical case, important case. And for example, for this inequality, open question is that to check if in this critical case, if that inequality holds. But if one applies some other more deep techniques, then one can cover, for example, when there are no weights here, and A, B, they are 0, then yes, then one can apply, one can prove answer to this open question for critical case, but for with weights, still critical case open here. Now, other inequalities. So this is another important function inequality, the so-called Gagliardi-Nuremberg inequality, and we have a weighted version, but this it's the same weight. So important consequence of our technique, and some small other one needs to not this line, but one needs to have some change in proofs. So also, like, it's not difficult to get this inequality 7, and this is important inequality, and it's also new because we are talking about variable Lebesgue space. And another important inequality is Poincaré inequality, and again we follow the same approach. Again, I repeat again, these inequalities, all these inequalities, they follow from the Steinweiss inequality. So, but the different deriving, different tricks applied to derive each of these inequalities. So here we have a generalization of the classical Poincaré inequality, and some call it Poincaré-Wirtinger inequality. But the idea is that we have we have here on the left-hand side in norm, we have this average of f, and classical Poincare inequality. There's another version of classical Poincare inequality without this subtraction, right? That's also true in if we talk about classical inequality, then that inequality is about Dirichlet problem. So when f is 0 on the boundary, but this construction is important to apply these inequalities to Neumann boundary conditions. So as I mentioned, main applications of the theory of variable Lebesgue space in the study of PDE, especially those models related to non-Newtonian fluids, study of dynamics of non-Newtonian fluids. And, so when you apply this, if you want to apply these inequalities to some models, then there's boundary conditions are important. So one really needs to generalize this version as well. So again, there are some. I tried to simplify these expressions, but well, some discussions there are also in our paper, but one can consider, for example, we are saying only this omega, and in omega this log Hilder continuous functions, but one can replace that by some Rn, and then to compare, because here we are, if we return back to these inequalities here in classical analysis, we focus on f, right? So f is our variable, but here together with f, and also we have another functions p, q, and 1 also can play with these conditions, relations, and to write different versions. But well, I believe in this case, another question is, of course, what happens if one replaces this a, b constants by some variable functions, but these are all these are interesting questions. But again, we have this critical case not included here, and that's open, and a particular case when we have the same norms, and here and there the same p, and without these weights, then there is a result. But again, the technique doesn't give us the critical case, so we are missing here critical case. All right, so our next results about fractional versions, and we, as in classical case, we replace now what appeared here in Rayleigh inequality. In classical Rayleigh inequality, we have a Laplacian, and now we replace that with fractional Laplacian, with in this whole range. So if you take S1, then indeed it gives on the left-hand side a Rayleigh weight So, and on the right-hand side, we get Laplacian. So that's indeed direct generalization of classical relief inequality. And this inequality was proved in one-dimensional case by Edmonds and Lebesgue, but we didn't find in literature multidimensional case. So here we have multidimensional case, which obviously extends one-dimensional case in variable Lebesgue space. And also, well, if here S is 1/2, then on the right-hand side we get. That's another question about. Well, there was this Kato conjecture about the classical one, and if we can replace that. Well, in classical case, yes, we can. But I'm not sure in this case if we can replace that 1/2 by a gradient. But still, this is. This is indeed about a version of Hardy inequality when S is replaced by 1/2. Then on the left-hand side, we get Hardy weight, right? Because it's just -1, and that indeed, that's about Hardy inequality. And also this range meets with the Hardy range. If we take here 1/2 in the numerator instead of S, then we get exactly the N. That's all right. Now, Karapetyants inequality, and well, this is generalization of previous inequality, and one can start from here, right? But we are following that classical order. So this is the generalization. Remember, I was talking about some GFA papers, and this. Okay, let me quickly. So this is fractional. Well, comparatively very recently approved fractional version of Karapetyants inequality in classical Lebesgue space, and now we obtain these inequalities in variable Lebesgue space. So that's, and as a result, which follows the same approach. And so this is fractional Karapetyants inequality, and these range, they agree with the classical one. And again, we cannot cover critical case when here, for example, when P minus is 1. Now here we have a fractional version of Gagliardi-Nirenberg inequality, and I guess maybe I had some typo there, but okay. So this is, it seems I have typo here, but this is weighted fractional Gagliardi-Nirenberg inequality, and again, same, we apply same technique. Now, as for application, as well, there's very one of initial motivations to study these function space about the PDEs in this form. On the left-hand side, we have some generalization of classical P Laplacian, and in turn, these expressions are related to some Lagrangians and related to some dynamics of non-Newtonian fluids. But here we have PD, and we are on the right-hand side we have nonlinearity, And a condition here, a boundary condition, is the Neumann boundary condition. And so we are interested in the existence of weak solutions to this problem. And indeed, one can apply the Poincare inequality we obtained in a variable Lebesgue space to show that there exists a solution to this Neumann problem, and under some essential conditions. And well, one can show that one can construct concrete examples. For here we have some general Q matrix, function valued matrix, and well, we have freedom of P, right, and B. So one can see that when indeed this assumption is about Q and about P's, they can be easily verified, and one can construct, for example, this. I think it's non-trivial, some non-trivial example. So, for example, in 3x3 case, one can construct this diagonal matrix, and so this is an example of applications. Of course, as in classical case, these basic inequalities, they should have applications. So to demonstrate that we have chosen this system, and then yeah, it can be applied. All right, now I think, yes, I have a few minutes to finish. So as I mentioned, so this is some approach, a simple approach, and to attack, to try to prove Stein-Weiss inequality in a given space, and then to derive all the other inequalities, starting from Hardy inequality to the Nirenberg inequalities in both fractional and the non-fractional case. Now, there is another important extension of LP space, and it's so-called Morrey space, well-known space. And here this is, well, there are equivalent definitions. So we have a Morrey space, some call it global Morrey space. So again, one can easily see that this, well, if lambda approaches 0, then easily we get here LP norm, right? So this is another generalization of classical Lebesgue space. And recently we obtained in this space the Stein-Weiss inequality, and in so-called Adams type, because this upper index, it's sharper version, so upper lambdas are the same here, and we proved this inequality. But here we are talking about constant, well, it's classical Morrey space, right? So well, motivated by this work, we tried, I think successfully tried, the technique we applied in this paper. The main idea is about to obtain these inequalities about after, of course, there's boundedness results for maximal operator and the risk potential, they are there. And we well, based on those results, we introduced some, I would say, iterated Hedberg type trick, but iterated one, and so that worked well. And so if we want to follow the approach we developed for variable Lebesgue space for variable exponent Morrey space, then we need to obtain Stein-Weiss inequality, right? So that's our the main target, and then from Stein-Weiss to derive Weiss inequality. So we needed to construct Stein-Weiss inequality, and as far as we know, there is no Stein-Weiss inequality in the variable exponent Morrey space. So here we have a definition of variable exponent Morrey space, and we are talking about here bounded omega, and that's, well, there are several versions, definitions for variable exponent Morrey space. Technically, the main difference is the following. One can define this space putting this lambda x inside the integral as lambda y. So that makes, well, in constant exponent case, both formulations that they cover constant exponent cases, but well, for technical further developing theory, it makes big difference. They are two not equivalent definitions. So we use this definition of variable exponent Morrey space, and then to obtain Stein-Weiss inequality in variable Morrey space. So this is our main result in progress. This work is in progress, and now since we have this inequality 14, now we follow exactly the same steps as we did in our previous paper for variable Lebesgue, but obtaining this inequality 14, this is so indeed the Stein-Weiss inequality. It is, I would say, technically it's difficult, and we are trying now to understand this inequality in unbounded domain. So problem here we have is that we are able to prove this inequality only for bounded domains due to definition, and because to introduce, there is several, as I mentioned, there are several approaches to introduce these variable exponent space. So if we follow this definition given by Almeida, Hassanov, Samka, then there's Stein-Weiss inequality, and as in previous case, in first part of this presentation, all the other basic inequalities, they follow from this inequality, but for bounded domains. So now currently we are working on unbounded domains, but this is our current collaboration with my colleagues. Thank you for your attention.
Well, thank you, Professor Durvudkhan, for very nice presentation, and we have several minutes for questions, if any. So you can raise your hands. You can go ahead and ask questions also. Well, meanwhile, I don't see hands. May I ask just a very simple question? I was surprised when you said that you can put r to the power lambda inside of integral, so you would have r to the power lambda of y. Yes,
Yes,
but
that's roughly speaking, yeah.
it would be very different space. I'm not sure that
Yes.
I understand how it would be related to Morrey space.
Well, it is, but the thing is that if lambda is constant, right? In
Yes,
that
you can
case,
put
yeah,
inside, outside, no more, no
yeah,
problem.
outside. So that would be different space, but still, it can be called Morrey space because in constant exponent case, it coincides with Morrey space. So
Yes, yes,
yeah, that's the
but
approach.
you know,
Kokatishvili, Professor
yes,
Kokatishvili,
I
and
know. But
yeah,
basically, this means this lambda is the radius of a ball to certain power. So when you put inside, you change power. You don't take radius at point lambda of x at the center of the ball. Then you
yes,
will have lambda of y, which is not related exactly to center of the ball. Okay, but I agree that it can be kind of extension
yeah,
of
it's
this.
complete. Yeah, I agree with you. It's different, completely different space, and yeah, that's why
And one,
I was telling that uh, I was telling that they are not equivalent.
I see their
And
hand. I see the
yeah,
hand by Satish, but maybe just one more little question before I pass the word to Satish Kumar. You know probably there is a more or less recent book by um, Lars Persson, our friend Lars Persson, and
uh-huh.
some other guys on Hardy Space. You know this book? I mean,
I,
it maybe just 5 years ago, or maybe 4 years ago, it appeared.
uh-huh. Yes, but it's is there like variable space?
No, I'm not sure that they have variable space. No, just
Okay.
just wondering. Okay, but Satish, I'm happy to see you. So please go ahead.
Hello, hi, hello, Professor.
Hello.
Hello. I'm just wondering, like, can it be possible to extend these results? Can it be possible to extend these results in the settings of Orlick spaces?
That's interesting question, important question. So our suggestion is the following.
Okay,
Please check if this version of Stein-Weiss is there. If with this full range, I mean, some particular case might be there, but with okay, let me return back to the Stein-Weiss inequality. So if this inequality is there, then then yeah, then or one needs to try to obtain this inequality there, and then over the basic all other inequalities.
okay. So maybe I'll write to you. Yeah. So I was thinking like something like I'm basically working in approximation theory. So like I thought we can try to extend something in the settings of Orlick spaces.
Yeah, that's a very interesting question. Yeah,
Yeah.
definitely. All this
Thank-
space is the important ones, and the question I think is important.
Yeah. So it's because it's also basically that the extension of LP spaces.
So we are like promoting this simple idea because in these function space, many papers dedicated, for example, on the Hardy inequality or Sobolev inequality or
Yeah.
Poincaré and so on and so forth. But
Yeah.
here, the simple idea we are offering is that to unify all these inequalities.
Okay. Okay. Thank you.
Thank you.
It was interesting talk. Thanks.
Thank you for your question.
Thank you.
Yeah.
Maybe more questions? Well, we almost run out of time, but It was a really interesting talk and with some applications. And I see that the theory is still developing. It is in the process. We were happy to open our session. I mean, this year, academic year. I mean, seminar with talk by our friend Durvudkhan, and Vladislav Kravchenko also says his regards. Well, I congratulate everyone with the new academic year. We had very good start. We had very good seminar, and thank Professor Durvudkhan again for your very nice, valuable participation.
Thank you for having me. Thank you.
Thank you everyone, and see you in 2 weeks.
Yeah.